Welcome everyone. Good afternoon. Today we have Professor Arun Paramekanti. He is a renowned condensed matter physicist and professor at University of Toronto. He did his B.Tech from IIT Mumbai and Ph.D. from TIFR Mumbai in 2001. And he did his postdoctorate from the University of California, Santa Barbara, and also from the University of California, Berkeley. After that, he joined University of Toronto as assistant professor and in 2005, and then he continued. Now he is a full professor, and he has many prestigious fellowship and uh, awards, including the Vajra Visiting Professorship, Fellow of American Physical Society, Sloan Foundation Fellow, Early Research Award from Government of Ontario, and Connaught Foundation Award from University of Toronto. And his research spans quantum material, strongly correlated system, and topological phases, and he has made seminal contribution in understanding of quantum spin liquid, multipolar magnetism, and spin orbit coupled system, including the theoretical prediction of octopolar order in Mont insulator. With this, I request, and he is going to talk about very interesting topic, almost failed magnets, ordered state on the brink of liquidity. With this, I'll request Professor Arun to give the interesting talk.
Okay. So thank you, Manoranjan, for the invitation and for this very kind introduction. So this will be a talk which, I'll try to keep it accessible to hopefully to also graduate students in the audience.
Arun sir,
And,
may I record this talk if you don't mind?
Sure, yeah, that's fine.
Okay, thank you.
Yeah. And it's kind of appropriate that I'm kind of do I need to do anything at my end, Manoranjan?
No. Please go ahead.
Okay.
Yeah.
Okay. So this talk is also, I mean, it's appropriate given that this work, actually part of at least the work that I'll talk about, started when I was visiting the SN Bose National Center, visiting Tanushree and discussing with both her and Manoranjan. So this talk will be based partly on the work that we started when I was there. So let me just begin with kind of a broad introduction. So when we think about quantum materials, we can think of simple magnets or magnetic orders. So for example, if you have a ferromagnet, we can have this cartoon picture in mind where all the spins of the on different atoms on these lattice sites all point in the same direction. And this has a very clearly observable macroscopic consequence, like this thing will stick to your refrigerator, for example, these days. But this is something that was easily observable, that people kind of had this, had this idea that, oh, there are these interesting, what they call lodestones, which kind of have some interesting character to them way back, before anyone knew about solid state physics or quantum mechanics or any of that. Right? But it took many years, many centuries and millennia before people realized that there can also be other types of ordered states. In particular, it took the invention of things like neutron diffraction before we could probe magnetic moments on the scale of that vary on the scale of an atomic spacing. And so even though these are somewhat simpler patterns compared to things that we will encounter later on, it still took a long effort to kind of uncover these patterns. And what one needs then is somehow to be able to see these kinds of orders or see patterns. One needs to be able to develop new tools and new probes. There's an interesting transitions on this one. So what happens when we look at quantum spins? And I hope these animations work. So one thing, of course, is that you might say, well, if this cartoon picture that I had here was really thinking of spins as just classical arrows, right? Or things that point in some direction. But if you think about quantum spins, you might, one potential way to think about this is say maybe the ground state order can still persist for quantum spins. And this was a big deal when the antiferromagnet was discovered. And one should think about small quantum fluctuations around this state. And if you can see this animation, what this means is that, spins can coherently precess around the local magnetic field that they see from all their neighbors. And so in particular, you can have some kind of coherent motion of spins across the entire lattice, which can form spin waves with different momentum. Okay, and so these are called magnons, or the quanta of these spin waves are called magnons. Okay, and at leading order, these spin waves will have some dispersion, which at low energies for an antiferromagnet. For a ferromagnet, it's quadratic. For an antiferromagnet, it's generically you have some linear dispersion starting from the gamma point, which in this case is kind of the center of this hexagonal Brillouin zone. And you get some number of linearly dispersing modes whose number and degeneracy sort of depends on the precise form of the order. Okay. All right. So if we turn to sort of another extreme of how spins can order, then this is a picture that goes back to Anderson and Fazekas and many others. Is you can kind of think about a system where instead of spins forming the kind of long-range classical ordered states around which you're thinking about weak fluctuations, is you say, well, I know that spin halves can form nice gapped singlets with, for example, with their nearest neighbors or maybe with their next nearest neighbors. And you can think of a state of these spins, which is called a quantum spin liquid, where instead of a single such state where spins pair up with some neighbor, you have some superposition which involves many, many of these states. So for example, the first one and the last one here are, you can have some kind of states of the sort where spins form these dimers, and these dimers can have some kind of liquid state so that there is no symmetry breaking at all in this problem. Okay. Now, these kinds of states in general, as you cool down, let's say from in 2 dimensions and 2 space dimensions, as you cool them down, they may not have any thermodynamic phase transition. So it may be very hard to realize that, in fact, there is some kind of hidden order of some sort here. And the other thing is that if you think about the excitations of the system, then unlike the spin waves that we saw earlier, you can think of taking a valence bond of the sort and splitting it up to form 2 spin half degrees of freedom, which, if they can move around freely, would in fact show that you don't have magnons, which are these spin 1 excitations that we saw earlier, but rather freely propagating spin 1/2 excitations. And so there are 2 limits in one which can imagine this. Either the 2 spin halves are so tightly bound, or in a sense that only spin 1 excitations are seen in any experiment, or in fact these spin 1/2 degrees of freedom do show up in some way in an experiment. So if that happens, then people refer to this as fractionalization. Okay. All right. So a convenient way to think about formulating this problem is in terms of what people call parton degrees of freedom. So in other words, so let me focus on the right equation here. You think of writing the spin operator in terms of some, in this case, fermionic degrees of freedom that carry spin 1/2 quantum number. So these are, up or down alpha. And the spin operator is written in terms of these parton degrees of freedom, which artificially enlarges the Hilbert space, because instead of having just 2 spin states, spin up or spin down, these partons are fermions. And so here in this case, I could think of either having an empty state or an up parton or a down parton, or having 2 partons at each side. Right? And so these are called partons in analogy with what we know from nuclear physics or from high energy physics, thinking about nuclei is composed of quarks. And you can now view this problem in this language, and you say, well, what is the advantage of doing this? And at least one advantage in the liquid state, or in this kind of resonating valence bond state that I was pointing out, is that fractionalization, which is that the spin half degrees of freedom are kind of explicitly revealed in this formulation. And now one can start asking, what do I know about the ground state of this interacting fermionic problem, this interacting problem of partons? And can I think about the ground states and excitations in this language? All right. So these are two extremes where people have thought about this. One is you take ordered magnets, and one is that you take spin liquids. And the question is, there are many magnets, which we will see in the talk, which are kind of on the brink of disorder, in the sense that on the brink of forming a liquid. So these are weakly ordered magnets, right? And there are many experimental systems which are of the sort, where the ordering transition temperature is much, much less than the typical scale of magnetic exchange interactions, right? And one can ask, okay, in this case, I expect that the ground state is conventional. It breaks some symmetry in the problem. Maybe it's magnetically ordered, like maybe it could be a nail state or some other stripe or incommensurate state. And the question is this parton formulation kind of useful even in these kinds of situations, right? And the question is, what is the nature of fluctuations? Can we say something about dynamics? Are there any experimental consequences? Okay, so that's the main part of this talk. We'll kind of focus on that. Okay. And so this is work, I should acknowledge that this work was done in collaboration with a number of people. So at Toronto, my students Anjishnu and Srikar were involved in this. In fact, Anjishnu is involved in both parts of the talk that I'll discuss. At SN Bose, where we started some of this work on honeycomb magnets, this was work done in collaboration with Manoranjan, with Tanushree, and with a student of Manoranjan, Manodeep, who is now graduating and moving to Japan to ISSP as a postdoc. And I couldn't find a photo, but Shreya Das was a student of Tanushree at that time when we started some of this work. Okay. All right. So with that, let me discuss the first part, which is these honeycomb cobaltates. So these are honeycomb frustrated magnets, at least a class of them. By the way, so just I don't know how this works, Manoranjan, but if people have questions, just interrupt and ask questions, because I really can't see if there are
Sure.
questions.
I will do that. If someone raise the hand, I'll let you know.
Yeah, or they can just unmute themselves and ask. Yeah,
Sure.
either way is fine. Either way is
Sure.
fine. Yeah, feel free to interrupt, is what I meant. There's no need to wait till the end of the talk. Okay. All right. So this, the interest in these honeycomb magnets actually grew out of the fact that there is a lot of interest in these so-called Kitaev spin liquids or Kitaev materials, where spins interact through some very unusual interaction. And in fact, thanks to Bhaskaran and others, I think more people in India have worked on it than probably in many other places. So I'm sure people are familiar with this. But the idea was, can one find material realizations of the Kitaev spin liquid? And in fact, among others, it was proposed that these cobaltates, honeycomb cobaltates, which have 7 electrons on each cobalt, could potentially realize this physics. And the crude argument for this is as follows, kind of sketched here, the microscopic kind of cartoon. Was that if I have 7 electrons in a system which has T2G and EG orbitals, then I can fill up 5 of them in kind of, in 5 up electrons, 2 down electrons. So I have 1, down electron that's left unfilled, or 1 hole in the T2G. And that carries, because of this threefold degeneracy, it carries effectively an orbital angular momentum L equal to 1. And now you can kind of read off from here that, I can have a spin 3/2 from here. because 5 of these cancel with 2 of them, so I'm left with 3 spin half degrees of freedom. And now I can combine these and arrive at a total angular momentum of 1/2, which it turns out is important as a starting point for having this kind of Kitaev spin liquid physics. So the idea was that this could be a potential candidate. And the question was, is this true? And one can ask this question because there is both, experiments on a large number of these cobalt-based materials, and one can ask, do any of them kind of fit this criteria for having Kitaev interactions between spins and possibly forming a Kitaev liquid? Right? An alternative, though, which is important to keep in mind, is that there can be distortions because in the honeycomb, you don't have an ideal octahedron. And if you split this degeneracy between the T2G levels that I had plotted earlier, in fact, there is another scenario where you again have 5 up and 2 down. So it looks like spin 3/2. But you've killed the orbital angular momentum by splitting this, because now this hole that's here kind of sits in a non-degenerate level. And if that happens, then you'd say, oh, I'm left with a pure spin 3/2 problem with no angular momentum. Right? And so one of the questions is to what extent is in the first limit or the second limit. And so people have done neutron scattering. So this is some experimental data from my colleague where you can kind of try to read off the local spectroscopy of this with neutron scattering, inelastic neutron scattering. You can kind of spot peaks in the signal. So this is just powder. So you integrate it over some range of momentum. And then you kind of plot the spectrum as a function of energy, and you see some peaks, and you can try and read off these peaks and associate them with kind of local energies of this problem. And this problem is very simple now. So you say, well, there is an effective L, which is 1, which I said earlier, an effective spin that's 3/2, and there is this distortion that breaks this degeneracy between these levels, can be encoded in a distortion scale. And now you can try and ask, is 1 in the limit where lambda is much, much larger than distortion, or distortion is much, much larger than lambda? Right? And it turns out, in fact, that we are sitting somewhere in between. Okay, so both these are comparable scales. And so neither picture is truly valid. And so one can start asking, what is the kind of exchange Hamiltonian that one expects in this limit? Okay. And so there's a large number of these cobaltate magnets. So, starting from, materials, which, and these are all kind of fairly symmetric ones. So these are rhombohedral magnets. These are somewhat lower symmetry. And it starts off by having, all of them have an exchange scale, which is in the range of, 5 to 8 millivolts. So that's about 50 to 80 Kelvin. Okay. But some of them order very strongly ferromagnetically. So they have like a 38 Kelvin transition temperature. So that's close to, maybe a little more than half of the exchange scale here. The ones down here have a different kind of order. So these are not easy plane, so this one has like in plane ferromagnetic order, but the adjacent planes are stacked antiferromagnetically. So there's like a stacked antiferromagnet where each layer is ferromagnetic XY order, in plane order. These ones form what is called a zigzag state, where spins on the honeycomb zigzag lines order along one direction, but the next zigzag line orders in the opposite direction. Right. So these are antiferromagnets. Nevertheless, you see that at these two extremes, you have ordering that's kind of somewhat reasonably well ordered. But there's a large number of these systems where the TC for the ordering is much, much smaller than the exchange scale, right? And what we found, and this is something that I'll mention, going on, is that in fact one can think of these as a direction where you increase a third neighbor exchange interaction relative to the first neighbor. So the ordering here is driven by weak third neighbor interaction, where the ferromagnet is unfrustrated. And then as you start increasing an antiferromagnetic J3, it turns out that it gets more and more frustrated at some intermediate coupling. And then at larger J3, you recover this zigzag order in the system. All right, so let's kind of ask about. So we'll kind of focus later on these, but to begin with, it's useful to ask what happens in the simple case, right? What do we know about excitations in the simple ordered magnet? And so people can measure this with neutron scattering, and we'll kind of contrast this with results later on where you can do this in the examples where they are more frustrated. Okay, so in the less frustrated one, what is seen is kind of fairly clear magnons. There's nothing else, but you see very, very clear magnon dispersions, which you can model very nicely with this kind of XY ferromagnetic order ferromagnetic exchange, where the XY exchange is ferro on the scale of about 4 millivolts. Right? And the interlayer exchange interaction is very, very weak. The Ising component, the Z, is also very small. Okay, so this is predominantly like an XY ferromagnet for all practical purposes for the in-plane physics. Okay, so this is sort of just comparing experiment and theory, showing that, okay, you can kind of recover these magnons. Some of the interest in this came from, looking at, crossings of this sort where you get analogs of Dirac dispersions, but for magnon excitation. So there was some interest in this some years ago. So it was in this context that we had kind of looked at some of this systems. Okay. But already at that point, it was clear that this is not a gapless system, because if you look at the excitation spectrum, as I said, if it was like an antiferromagnet, you expect a linearly dispersing gapless magnon. And it turned out that you can kind of sit at certain momenta and see these dispersions, and you can ask, well, do those dispersions basically lead to something which is gapless and linearly dispersing and with a zero gap at zero energy, and it turns at the ordering wave vector, and it turns out that the gap is non-zero. And there is clearer data, that came out about a year later from Radu Koldea and collaborators, where again they could kind of map out this dispersion and find a gap. Okay. So this clearly hinted that, in fact, this simple XY magnet is not the whole story. And that there are interactions beyond this XY model. And in fact, this is something that got us interested, and we worked on it together with Tanushree and her student Shreya, where we combined kind of the DFT inputs from their group with sort of looking at diagonalization to calculate sort of exchange interactions. And what we found was that, certainly there were these XY-like exchanges, but in addition, there were weaker off-diagonal exchanges in the system, which we found could kind of induce gaps in the spectrum that I was showing earlier. Okay. So this idea that, okay, these are more or less XY-like magnets, but with weak anisotropies, but one can kind of understand the excitation spectrum. Okay. And so now let's move on to another interesting example where we looked at something which where the ordering transition temperature is very low. So these are ordered, but maybe they are on the brink of forming some kind of liquid state where the transition temperature should in fact be suppressed to zero. Right? And in fact, initial suggestions to this from the experimental side came from experiments from Bob Kava's group, where they looked at this material, this cobalt honeycomb magnet, and these spacer layers make these much more quasi two-dimensional than the ones that I was showing you earlier. And in a weak field, they argued that whatever magnetic order is there, in fact, goes away. And they conjectured that it could be possibly some kind of Kitaev spin liquid driven by a weak field. There was similar, suggestions from sort of experiments from Tyrell McQueen and Natalia Richko in Johns Hopkins, where they said, okay, you can try and drive this magnet to a state where the magnetic order disappears, perhaps by doping with some thing. So this doesn't make it conducting. This is still an insulator, but the magnetic order is suppressed at least by a factor of 3 or 2 or 3 in terms of TC. And so the question is, is there some interesting spin liquid, here or here? Right? And so that was kind of from just looking at the transition temperature and susceptibility, but there were then experiments that started looking at other questions. So for example, you can look at the dynamic response of the system using terahertz spectroscopy. So what this measures is you're looking at the fluctuations of Sx and Sy. So you imagine sending in light along the third axis of the crystal, along the c-axis, coming down the c-axis, where there is a magnetic field of light that can perturb the spin system. And what that can do is it can probe the in-plane fluctuations of chi, of the spin susceptibility. And so they can plot sort of chi double prime, the absorptive part of the spin response as a function of frequency, but now in this terahertz window where 1 terahertz is about 4 millivolts. And what they find is in the ordered state, which is in this dark blue at low temperature, you find evidence for peaks that you can associate with magnons in the system. But when they go just a little bit above TC, to TC is about 5 Kelvin. So already by that, if they go to like 5.5 Kelvin, so it's just a little bit above TC, they find that there is this very, very broad response in the system across now across a range of temperatures. So you get this kind of broad response. And one way you can kind of think about this is you say, well, I have some fluctuating spins, and I can probably think of some classical fluctuations induced by thermal disorder in the system. Right? So that's one way you could kind of potentially think about this. This is not the way that we'll formulate it, but this is one potential way to think about this. The other thing they've done is experiments where you apply an in-plane magnetic field as you do this spectroscopy, and they find that what this does is it takes, so this is now at a fixed temperature, but as a function of increasing field, and you find that this, broad power law-like spectrum now starts developing kind of a gap as you apply a larger and larger in-plane magnetic field. Okay. So these are experiments where you can do some spectroscopy to infer that magnons are gone, but they're instead replaced by something that has broad excitation spectrum, and this is at 0 wavelength. Okay. And now you can do something else, which is to try and measure the thermal conductivity. So you can ask, well, what are these, these things that carry energy can also, have some, some spin, and they have some energy. But you could also ask about thermal transport. So you measure the diagonal thermal conductivity, so kappa XX. And what you normally expect is in an ordered, well-ordered state is that kappa XX as a function of temperature will come down to 0 eventually as T goes to 0. But instead, what they find is that there is some residual thermal conductivity depending on, so these are different samples of this same compound on which they did these terahertz measurements. And what they find is that, okay, admittedly, this is a bit, there is data from other groups, but this data, if you extrapolate from, temperatures of about 1/10 of a Kelvin, you extrapolate down and you find that there is some window of parameters where it looks like it extrapolates to a finite kappa over T, non-zero kappa over T. And this usually signals some kind of metallic state. So if I take a metal and I measure kappa over T, then it would extrapolate to a non-zero value as temperature tends to 0, right? So this looks very much like there are some kind of metallic thermal transport, except this is some insulating magnet. And there is similar results on a different cobalt-8 where, this is on some slightly different, well, it's similar temperature window. And they do this extrapolation, and again, they find that this extrapolation gives rise to something that's non-zero. And in fact, these numbers look a little bit different by about a factor of 10. So this looks 10 times larger than this one. That just turns out because, they're using just different units here, right? So one is milliwatt per Kelvin square centimeter, the other is watt per Kelvin square meter. So it turns out that, in fact, these two different compounds, which are both honeycomb magnets, have very similar residual thermal conductivity to less, within a factor of 2. Okay, so this is like some very small difference between. So this is about 0.04 in these units. This is about 0.05 in these units. So they are very, very similar. So that's one strange thing. Okay. So then with Tanushree, we had kind of asked, if you take this other magnet, what changes? And that's when we discovered that, in fact, in addition to this, nearest neighbor ferromagnetic exchange, there is a fairly large third neighbor anti-ferromagnetic exchange that can frustrate this magnetic order. Okay. And so we can kind of ask, what does this do to the physics of the system if you have a ferromagnet that's frustrated by this anti-ferromagnetic exchange? And in fact, Manudeep and Manoranjan had done these calculations using exact diagonalization and DMRG to explore this physics. And so if you look at increasing J3, ignore the y-axis because it's not important for what I'll discuss, and you pick some xy, xxz anisotropy. So this is the value of the z exchange relative to the xy exchange. Okay, so there's some degree of xy like anisotropy because this is less than 1. And what you find in exact diagonalization on somewhat smaller system sizes is that you go from a ferromagnet, an easy plane ferromagnet, to this kind of easy plane zigzag order that I mentioned that is relevant for some other materials, via an intermediate state, which at least on these small systems seems to have some kind of liquid-like correlation. So there is nothing, so if you look at spin correlations, it doesn't look like there is any preferred sharp wave vector that emerges in this window. Okay. And now you can kind of ask, can one do a larger system size? In fact, so their group had done DMRG on this. On system sizes which were as large as about 70 sites, 72 sites in different geometries, and the basic conclusion was that at least on these system sizes, the ferromagnetic order, which is plotted in blue, kind of disappears from looking at spin correlation, disappears at about 0.3, which is kind of not very different from this ED result. The zigzag order kind of starts taking off beyond some point, but there is a window again where these DMRG studies are consistent with the no magnetic order being seen in the system. Okay. There were reports somewhat later from a little bit later from Sasha Chernishev and collaborators, where they claim that in fact they find some kind of Ising-like order if they go to much, much larger system sizes. But there were some issues with this study, which I won't dwell on it, but it's not obvious that this is true, and certainly there was no sign of this at all in any of the other studies that we've looked at. So it's not very clear what the fate of this. So there is a small window where at least on system sizes explored in this work that we did, it looked like a spin liquid for all practical purposes. And then the claim is if you go to much larger systems, maybe there is some kind of weak ordering in the problem, right? So that would be consistent with the story of a system which looks liquid-like, but probably has some weak magnetic order. Okay. And again, there were other studies. So there's some functional pseudo fermion functional FRG, where studies where there was some evidence of liquid-like states possibly present in the system, or it could be weakly ordered because you're close to some transition between incommensurate states and Ising-like order. So there could be some regime here, which in fact could be liquid-like in the spin half problem. All right. So with that, we kind of had work with my student Anjishnu, where we were looking at sort of parton wave functions with Anjishnu and with Srikar, where we take this parton state that I was telling you about earlier, and now you can ask, well, can I write down what is the optimal kind of parton wave function once we do numerical projection to satisfy the constraint that there's exactly one fermion at each side. So you write down some parton state, some wave function of these partons, and you can numerically project it to having one electron or one parton per site, and ask, well, can I find what kind of parton Hamiltonian best describes the ground state of the system? Okay. And it turns out that the answer is that, at least in this intermediate window, it turns out that the best wave function that we found is when we take these, partons which hop on the honeycomb lattice. So of course, this is an underlying honeycomb lattice. Because there is J1 and J3, there is some first neighbor and third neighbor hopping of these partons. And the ratio from the numerics is that the ratio is about 0.2. So the third neighbor hopping is roughly like 5 times smaller than the first neighbor over a wide range of J3. Okay. And now, you can have the important thing here is that usually if you have these spin up and down electrons, think of these electrons, if they hop with the same hopping sign, you will have something which is spin rotationally invariant, which is not the case that we have. But if you have spin up and spin down that hop with the opposite sign, so let's say spin up hops with plus T1, then spin down hops with minus T1. And it turns out that that is the optimal solution. And in fact, that's perfect for describing magnets with a tendency to have easy plane order rather than SU2 Heisenberg-like symmetric magnets. Okay. So this one, in fact, if you look at the dispersion of these partons or these electrons or these partons, looks like exactly like graphene. So it has Dirac points at the K and K prime valleys at the corners. And it turns out that this ansatz, in fact, if we compare the energy with exact diagonalization energy is here as a function of J3, there's this window where these states with this kind of Dirac spin liquid, but with weak magnetic orders of various sorts, all have an energy which is within like a few % of the true exact diagonalization energy on this 24-site cluster. And then as you move away from this point into the ferromagnet or zigzag, you can take this Dirac spin liquid and impose weak order on top of it. And as you move further and further in the two directions, this order gets stronger and stronger. So by the time you're here, you're in a Dirac-like state, but with the order so strong that you probably lost all physics of this Dirac problem here. By the time you're deep here, again, this ordering is so strong that you've lost all sense of that it came from some Dirac partons. But the expectation is that somewhere in this vicinity, this Dirac parton physics is still a useful starting point. Okay. So now we can start looking at sort of what does this imply for experimental consequences of this, right? So this is the parton band structure that I was showing you, and as a function, so in this Brillouin zone, you get these kind of Dirac-like crossings in the band structure. Right? But it turns out that in fact the low energy excitations of these partons, you can see is that I can make excitations now where spin excitations correspond to excitons like in this parton description. So it will be like a particle hole excitation. And if you do that, then you find that there are lots and lots of low energy excitations here in this dispersion. And they give rise to a flattening of, so unlike graphene, which has a relatively isotropic velocity around this crossing point, T3 actually leads to a flattening of this dispersion along the edges of the Brillouin zone. So you get something where there are low energy excitations around the entire hexagon, which of course, but still with Dirac crossings at this point. So it's just that the velocity in these two directions is very, very different. Okay. And now you can try and use this to compute sort of what the spin response is, just ignoring gauge fluctuations entirely in this calculation. And you can ask, well, what does the spin fluctuation spectrum look like in this parton language? And what we find is above some threshold below which they really can't measure in the experiment, this kind of broad tail that's seen in the calculations in fact, is consistent with this broad tail seen at low temperatures in the experiment. And then the experiment, as you heat it up, these response goes down, and that simply comes from the occupations of these different fermionic states here. Similarly, if you apply an in-plane field, it turns out that you gap this Dirac spectrum with an in-plane, uniform in-plane field. And what that does is basically dig out this gap, again, consistent with what is seen in experiments. Okay. So even though this Dirac partons might seem very far from sort of this spin wave theory, it does capture certain aspects of the experiments that we've seen. Okay. More importantly, you can think of weakly disordered Dirac fermions and try and ask, well, what is the thermal conductivity that you expect from this kind of weakly disordered state? And this is the calculated, thermal conductivity, or kappa over T, and this is per layer in this calculation. So we just assume that there are isolated planes that contribute to this. And if you want to get the 3D transport, you would just have to, multiply by a suitable factor of or divide, in this case, going from here to here with a suitable layer spacing factor. And what we find is that over a broad range, if you broaden the Dirac dispersion by a little bit, assuming that this comes from some disorder which we don't explicitly model, then in fact the thermal conductivity that is, the experiments are in this band here, based on data from these experiments, and the theory kind of falls within this range here. So the blue is the Dirac spin liquid, and then if you put in some amount of order, like for example, if you put in some weak ferromagnetic order or weak zigzag order, then there is some regime where this weak order and disorder, or this broadening, conspire to give you results which are very close to the experimental result for kappa over T. Okay. Certainly to within a factor of 2, it's consistent. And so now the question is there some merit to thinking about this physics in terms of weakly disordered Dirac spin liquid as a starting point to think about the physics of thermal transport and other probes in the system. So one thing that's interesting is in fact that if you think about Dirac systems with this kind of weak broadening, it turns out that the thermal transport, the result for kappa over T, in fact, is a universal number, which just depends on how many Dirac nodes there are in the problem, etc. And so in fact this result, and we'll see this something similar when we look at the triangular magnets next, is that these results in fact seem to be not very crucially dependent on the precise system. If you have a Dirac spin liquid, in fact you should expect something very similar if they have the same number of carriers. Okay. Right. So with that, let me kind of switch to, on the same theme, talk about some more recent work that we've done with my student Anjishnu on looking at frustrated triangular magnets. Okay. And so just as there were many of these, cobaltate magnets that I was showing you earlier with honeycomb geometry, there are many of both cobaltate and more recently some ytterbium-based magnets, which are all pseudo-spin half. So you can think of them as some spin-orbit coupled magnets. But the spin-orbit coupling to a large extent is described by some kind of XXZ model. So this is Heisenberg, but with anisotropy that could be weak, that makes it either Ising-like or XY-like, depending on delta being greater than 1 or less than 1. Right? And so many of these magnets, again, if you look at the exchange scales here, they're on the scale of, in this particular example, of about 20 Kelvin. The ordering is at about 3 Kelvin. So this is an example where the ordering scale is much less than the scale of the exchange. And certainly if you calculate the Curie-wise, it's a much larger number. And so, or, it's similar number. And this one here is much, much smaller. There are other magnets, so there are some cobaltates which seem to have a much smaller exchange scale, and these have again ordering temperature that's much, much weaker. So this one is more little bit XY-like, close to Heisenberg, but a little XY-like. This is somewhat more Ising-like magnet, where the Z exchange is bigger than the XY. And then there are others where these ytterbium ones, where again, the best as I know, they actually don't find any evidence for order at all. So this might actually be a spin liquid in the ground state of the system. Okay. So these are other class of systems where again you can think of, possibly weakly ordered magnets, or in fact in this case they claim it's in fact a ground state spin liquid. Okay. So what is it that we can ascribe? So at least in some of these, what people can measure is look at something like specific heat, and once you subtract off the nuclear and lattice contribution, the claim is that there is some residual power law specific heat. I mean, this is tricky because it's over a not very large range in temperature, and you have to do sort of subtractions to extract out this T square. So I don't know, it's not very clear to me how reliable these are. But okay, this is the best type that they can do with this with these systems. There is similar, on one of these, there is thermal transport measurement. And again, if you look at kappa T, it turns out if you go back, it turns out it's very similar in magnitude to what we saw earlier with the honeycomb magnets. Okay. And now there is a lot of neutron, inelastic neutron scattering. And what is interesting is that if you do simple spin wave theory, you find these white lines that is shown in the here, the theory plot. The experiments find kind of that these modes are not, like this, they're in fact pushed down. So at the M point of the Brillouin zone, in fact, there are somewhat low energy excitations. And in fact, there's a lot of continuum scattering here that's seen in experiment that wouldn't be captured by a simple spin wave theory, right? And this M point minimum is also found in other magnets, not just in this one. There are other systems as well. Some of these other triangular ones where again there's a pronounced minimum at the M point. And so these exist in addition to these diffuse, these features exist in addition to kind of sharp looking modes in the system, right? And so now one can kind of ask, is there a usefulness to again using this Parton description to think about this physics? Okay. So what do the numerics say? So there is recent work where people have looked using DMRG, again from Sasha Chernishev and Steve White and collaborators, where you can kind of take the triangular lattice, take a model which has both J1 and J2, both being antiferromagnetic, and now go where you tune delta, this anisotropy, so that you could either be in the easy plane limit or the Ising limit as you go down here. And what is found is that there is certainly an intermediate window where there is evidence for liquid-like physics, where J2 gives rise to a regime where you don't have the simple 120-degree order of the nearest neighbor antiferromagnet, nor sort of the stripe order that emerges in the larger J2 regime, but there is this intermediate. So if you take a cut along here, the story would be somewhat similar to the honeycomb, where you go from some simple ordered state to a different ordered state via something that is, in this case, there is stronger evidence for spin liquid physics. And in fact, there is work from earlier work from Yasser, Iqbal, and others, where they had argued that in fact this intermediate liquid state has some kind of a gapless U1 Dirac spin liquid. At fairly small values of J2, this should emerge. So this was in the Heisenberg limit, where it's precisely along this line. And so with Anjishnu, we recently done VMC, where you go, this variational Monte Carlo, where you go away from this line, but rather look at delta, which was 1.5. So in this language, it would be sitting somewhere here. So this is in the somewhat Ising-like limit, but not deep Ising. And what we find is, again, that if you start here and you compare the energies of different states, there is a Dirac spin liquid with together with certain order, which is called pi order, so it's some 3 sublattice ordering here. And it turns out that that's the lowest energy solution here. If you compare these different colors, it turns out that's the lowest energy. Then there's a range of J2, which is not too different from here, maybe a little bit different from the precise boundaries that are found here, is that this Dirac spin liquid in the VMC seems to have the lowest energy. And eventually these energies cross such that if you take the Dirac spin liquid and add on top of it this stripe order, then that becomes the lowest energy solution. So in fact, there is a very similar picture to the VMC in the Heisenberg limit, even if you move slightly away from that precise Heisenberg point. And so if you do this, you can ask, well, can I start looking at this problem, not numerically, but can I do some parton-like theory to try and understand this physics of competition between magnetic order and spin liquid? Okay, and that typically in a theory with fermionic excitations is kind of it's been harder to do, to explore this in some controlled limit. And so we had kind of formulated a modified kind of large N formulation where we think of these partons as carrying not just a spin label, but some additional, you can think of it like an orbital label or something. And it turns out that there is a limit where you can tune now, the number, so people usually generalize the spin a half problem to like an SUN or SU2N problem. The SU2 to like an SU2N generalization, where when you go to large N, you recover kind of spin liquids. And then when you go to small n, you have magnetic order. And what you want to describe is this physics of how do you go from the spin liquid into the magnetically ordered state, right? But these are two limits which are very far from each other, right? And so by introducing the second kind of flavor label or this orbital label, one can try and define a deformation which is somewhat similar to what people have done for bosonic partons, where you have 2 degrees of freedom now, and you can tune them maintaining a fixed ratio that takes you along a certain line. And if you do that, then the physics at this large N allows you to describe both spin liquids and ordered magnetic states, and gauge fluctuations, which are kind of describing these additional interactions that impose the constraint of having 1 electron per side, are kind of corrections that will need to be included as you go away from here, right? So the dominant effect now is partons and their interactions that can give rise to some kind of symmetry breaking. And so if you do this, you can kind of look at what the dominant effect is. And the dominant effect, it turns out, is that you have to have some kind of RPA-like response. But these lines have some self-energy corrections that need to be included, which for simplicity in this first piece of work, we have not included them. So we are just now doing like, take these partons, take the free dispersion that we have from, as suggested by the VMC, and include kind of just bubble diagrams that describe the spin fluctuations within RPA. Okay. And what we find is that, so if you do this, let's say the large N, you can ask, well, do I get the right picture for the ground state? And it turns out that with a suitable choice of this ratio M over N, so this kappa would be 0.5 for a spin half. Here, by slightly tuning this ratio, you find that, in fact, you can open up an intermediate Dirac spin liquid window. So that's kind of consistent with the numerics if you do this. It turns out the ordered moments, and I don't have an explicit plot of comparison, the ordered moments that they find in the numerics is also consistent with this kind of large N calculation. And now we can start asking about the spin dynamics. And we find that, because these Dirac dispersions have, minima, which are separated by a wave vector that corresponds to the M point, this kind of spin liquid dispersion emerges naturally, where the RPA gives rise to, sharpish looking spectra at low energies, where these partons get bound into spin wave like excitations. But at high energies, you discover sort of that there's a lot of continuum scattering. And that's not kind of, too different from what has been seen in some of these magnetic systems. You do find evidence for sharp modes or sharpish modes near K, but there's a lot of continuum scattering here. And there is some evidence of, that you have some thing that's tending towards lower energies near the endpoint, which is consistent with the story. There's similar work on other cobaltates. Here it's less, the experiments are somewhat saying maybe there is some degree of disorder, or maybe these are just harder experiments to do given the energy scales. But again, we predict that there could be sharp modes that coexist with sort of low energy endpoint dynamics, and at least it's not inconsistent at first pass with these experiments here. And then these are some experiments somewhat more in the Ising-like limit, where what is shown here is you fix the energy and you're taking a cut through this in wave vector space. And this is data showing that the brightest rings appear around the corners, which is consistent with this calculated one that we have from the Spartan plus RPA. The next ones are kind of near the M point, which is here, and then you get this kind of other spots which are consistent with what is seen as the weaker spots in this experiment. So I'll stop here, and hopefully I've given you kind of at least a flavor that there are a lot of these new experiments on honeycomb and triangular frustrated magnets, where possibly the Spartan language can provide a useful description of the physics. We have this new formulation. I didn't talk too much about it, but there's this formulation which, if people are interested, we can chat more about these partons, which allows us to describe this competition between spin liquid and ordering, and think about the dynamics of these frustrated magnets. So with that, I'll stop, and if there are questions, I can take questions.
Thank you very much for an interesting talk. Let's have some questions. Yeah, Tanusridi, please go ahead.
Hi, Arun. Thanks for the nice overview. Maybe this large NM, I will catch you one day, understand more about it. But I have a different question, more from materials perspective. That it seems both for your hexagonal and triangular, since it is from transition, it appears at the transition between two ordered kind of magnetic configuration. It's actually a sweet spot, and it's a luck whether your compound will really fall in that sweet spot. So is there any experiment to kind of perturb any compound which is very close to it, either I don't know, by straining, by putting pressure? Has people tried to do that, or is that too difficult?
Yeah, so I actually don't know of. I think this strain idea is probably a good thing, because it might relieve frustration in some cases, and then or maybe make it more liquid, like I don't know, but either way would be interesting, I think. So apply strain, and maybe one can do certain spectroscopy. So I think neutron scattering would be hard, but maybe this this terahertz measurements on some of those, I think, might certainly be possible. So, or thermal conductivity or something, right? So I think that is interesting. I don't think it's been tried though. Best as I know, we have not come across anything where people have explicitly strained these to look for whether the ordering gets enhanced or not. Yeah, but that's a useful.
Like it's a sweet spot because it's happening between two ordered phase.
Correct. So that's right. So the only one that of course, we worked on this and others have, where you can apply like a weak magnetic field to try and see if you can push it towards more into the liquid. But you're right that maybe one could also ask, if you do something else, does it become more ordered and become more conventional? Yeah, that's a good point, actually. Yeah.
Okay.
Yeah. Next question, Anoopji, please go ahead. You have to unmute and then.
Yeah. Okay, Professor Arun, thank you for this informative talk. I have question similar line with Professor Tanushree, that for these honeycomb systems, you discussed there is a competition between J1 and J3. So we get a narrow range where the spin liquid state can be possible.
Right.
Yeah. So my query is, have you any idea about in-plane anisotropy, how it plays play a role on this kind of spin liquid state? If you add some in-plane anisotropy top of this J1 and J3 exchange, competitive exchange interaction.
Oh, right. So there is so we had some work, so Manodeep and Manoranjan had looked at this. Sorry, somewhat echoing. Is this okay? Or yeah. So there was, sorry, I kind of went over this quickly, but I kind of flashed this. So this thing here was looking at, so this limit where k is 0 is looking at the thing where there is no in-plane anisotropy. So it's like an XXZ model, right? With no, so it's rotationally invariant around the SZ. But then you include these, this version of, you can call these Kitaev or compass-like terms here, where you pick some fixed ratio of K1, K2, and you just vary this combination. So that has in-plane anisotropies. And in this particular case, it actually seems to shrink the window of this spin liquid. And in other DMRG studies, so this, we had not, I think, done explicitly DMRG with the K, with this anisotropy term. Okay, and it's not here either, unfortunately. But there is a paper by, so in this paper by Sasha Chernishev and Steve White, they've looked a little bit at that, and it seems to promote, this picture that you get some liquid that kind of shrinks, the window shrinks as you increase some anisotropy. So this lambda is not the correct one. This is the, this is the xy versus z. But there is some term here which, if you increase, does lead to a shrinking of the spin liquid window, and then possibly other orders that emerge at large values of this k. So we think we don't have a k that's that large. The in-plane anisotropies, might give you here. They are not something that will give you new ordering in the problem.
Okay, thank you. One more point. So have you tried to see the second nearest neighbor exchange interaction, how it is playing role? Because
yeah, we have not explored. That's a good point. We have not explored the full phase diagram because there are many parameters here. So there is J1, J3, right? So that's one ratio. There is this two types of anisotropies in the Hamiltonian, right? And then, as you point out, there could be weaker J2. So certainly from the DFT studies that Tanushree and her student Shreya had done, when we looked at those DFT inputs to try and compute these second neighbor exchanges, it turns out that they are negligible for the honeycomb magnets that we had looked at. Okay, but that's another axis that one could study. So one could look at kind of a more generalized Hamiltonian. That's a good point. We have not done that.
Okay, thank you, Professor Arun.
Okay,
I'm done.
Okay, thank you. Mayuk, Dr.
Yeah,
Mayuk.
thank you, Professor. Yeah. So thank you, Professor Arun, for the interesting talk. So one thing you mentioned that you have considered this weak order, right? So in your Hamiltonian, so can you just please enlighten that how you have input? So is there some sort of phase separation that you have considered that, okay, one part is showing some certain, let's say, conventional ordered state, and the other part is showing some sort of spin liquid state, something like that?
No. So the weak ordering here that we are talking about is, so think of a spin liquid, And now if you want to have magnetic order, the way we think about magnetic order in a conventional mean field theory would be to say, oh, well, I put on some local magnetic fields, right, that have the right pattern of symmetry breaking. Right? And now you could ask, well, how large is this Weiss field that's going to induce this ordering? Right. So what you could have is you could have a spin liquid with imagine some very weak internal fields in the problem that break symmetry.
So,
but they break symmetry throughout the crystal, but they're just very weak in magnitude. So that's the picture of this weakly ordered state.
Okay. So, and another point is that, as you have mentioned, so there are these boundaries, right? So is it like these boundaries are like rather sort of, if one, let's say, applying some pressure or some other tuning parameter going from one state to the another. So is it like first order type of change from, let's say, ferromagnetic to the spin liquid or to the zigzag states?
Yeah, so that's a hard problem, right? So certainly from the numerics, it looks like, if we look at something like this, we would say, oh, the order parameters seem to vanish smoothly from both sides. Now, in the Parton-like calculations, if you include fluctuations, you could potentially have even first-order transitions, right? So there is no, I don't think we have a clear understanding of it, even at this level. I mean, forget doing like the full field theory of this transition. But you can ask, well, if I take a Dirac spin liquid, what are the nearby states that I can access through a continuous transition? And I don't know if Shubhro or Yasser is in the audience, maybe they have an answer to this question. They've probably thought more about this, the theory of such a transition. But we've certainly not, so potentially it could be weakly first order. Certainly in these numerics, it looks like it's continuous, that the order parameters seem to vanish smoothly to zero from the two sides.
So yeah, I mean, I'm just saying in the sense that, okay, if it is really sort of first order weak first order, then maybe experimentally also the thing that have people, I mean, found that there is this kind of coexistence of spin-on dispersion as well as the magnon dispersion. So maybe that may sort of support that.
Right.
So
I see. So you're asking whether it's not that the magnons and spin-ons coexist homogeneously, but there is some patches, and what you're seeing in a neutron experiment is some combination of a little bit of this. Of course, you're measuring the entire system.
Yes.
And you could, I see, that's a good, that's a good point. I don't know if we have a way to, I don't know if we have a way to say something sensible about that, actually. Yeah, that's a good point. Yeah, so if you have a first order transition, you could have spin liquid that coexists with ordered regions.
Yes.
Yeah, sorry. Yeah, I don't have anything useful, but that's a very interesting, that's a good point.
Okay, thank you very much. Thank you.
But how big is the patch? I mean, you have to see that maybe.
Yeah.
Any other question? If not, I have one small question. In this triangular lattice, this rare earth compound, you had this. So do you have the magnetic susceptibility data? I mean, this attribute.
Oh, okay. Unfortunately, I don't have a slide with that.
Okay. So in some cases, what I see that even if it is a ferromagnetic in nature, so it's diverging at zero temperature, but still people say this is a ferromagnet. What is the reason for that?
Sorry, can you repeat your question?
So even if you see the magnetic susceptibility data, so what they show is that it look like a ferromagnetic kind of behavior. So at zero temperature it diverges, right? I mean, it's increasing as you go lower the temperature. So generally, I would have expected either like it's a paramagnetic or ferro kind of Yeah, I mean,
right. So in these, okay, so in these cases, there are, I think there are issues because there are, I think, I don't know if this one has nuclear contributions. There could be defects, which they say, I mean, they say that they have suppressed. So it turns out that in some of these systems, there is some degree of randomness because there could be some mixing of this zinc and gallium sites. And so the claim is that at least in some of these, there could be sort of exchange disorder between the ytterbiums.
I see.
This one, they claim that it is much less in this compound. So there are other ones where the claim is that, in fact, that's a strong disorder, that this kind of mixing disorder is much more relevant.
I see.
And so in those cases, the claim is, maybe you could have some kind of random singlet-like physics where there could be, weak bonds that somehow give you a strong response in the spin susceptibility.
I see.
Or there could be possibly some weak impurity spins that give rise to kind of this strong enhancement.
Yeah, but in that random singlet, till you have the singlet, you always have the like it goes to zero. But unless you have the free spins, if you have free spins, then it will go up because it behaves as if it is a paramagnetic state. Yeah.
Right. So that depends. Yeah. So if you're at a certain temperature, though, right? So at low temperatures, you might break some of these weak bonds, and you might expect that you could get some susceptibility, which looks like but if there are free moments, certainly down to the lowest temperature, if you want this, maybe you want some kind of free moments that are present. And so I don't know if disorder plays. Sorry, I don't actually have susceptibility data on this compound.
Okay.
But there, I mean, there is, but it's just that I don't have slides. But there are others where certainly disorder is thought to play like a much more important role. I think where zinc is replaced by magnesium, I think it's ytterbium, magnesium, gallium, O4. I think it's a different formula, and magnesium instead of zinc. And there, certainly disorder is thought to play like a much more important role in the physics.
Okay. Okay, thank you. Is there any other questions? No, if not, then let's thank the speaker for excellent talk and very informative talk. Thank you very much, Arun sir. And thank you.
Welcome.
And thank you very much for joining. And see you, everyone. Thank you for joining. Bye.
Thanks.